Okay, this is mechanical doing a very busy, challenging conservation of energy question. Okay, it's question number 1485. It's got lots going on. Okay, it's complicated. It's yeah. There's a couple of things in it where the author just assumes that you understand something, or otherwise, the motion is not debatable. But let's get after it. Here's the diagram, okay? And I'm gonna draw the diagram pretty big because I have to draw it. There's some geometry change in here, so we have this block, okay? Block like that, and it's on a surface, okay? And then there's a cliff or whatever. It's an edge like that, and there's a wheel here, a wheel right there, right? Like that, wheel A. And wheel A and block B are connected together with this link arm. Whoops, I missed it. Well, close enough. Okay, like that. And the system it can move. There's friction here, okay? In fact, that friction force is given as 20 pounds constant. That's a little bit of an olive branch from the author. Normally, of course, friction force is a function of weight and normal force, and it will also be a function of the tensile force in this angled rod and so on. But that extreme complication, which is what it would be, is headed off at the pass by just saying, look, the friction force opposing the motion of block B to the left is 20 pounds constant. All right, let's take it. Stop asking questions, just take that. Thank you, okay? All right, the question says, by the way, there's a few known things here. Here's a little known column, okay? Weight of the block is 60 pounds. Yes. Weight of the wheel is 80 pounds. Okay. Friction force 20 pounds given. Okay. Um, Now here's the thing. It's assumed by the author. Well, it's not assumed. It can be shown in the mathematics, but it's implied in the question that this system wants to drop. A wants to drop. There's enough. The friction and so on, and the weights of the objects are such that if A is released, the system is held here by rest. If A is released, it's going to drop and drag B to the left. Okay, that much is implied. In fact, it even says block B ends up to the left 6 inches like this, like that, which means that this thing is now down here a little bit, like that. Okay, and that wall's like that. Now, that's assumed. Although if that wasn't the case, the math wouldn't work out. The math, you get a negative energy value or something, and then you say, oh, negative energy. Well, that would imply that you've actually that it's not. It wouldn't be in motion. That when you release the system, it just sat there. The friction force at B was too great for this to overcome. Okay, but it's not that way. The book obviously is not going to give you a question that has nothing to calculate or no motion. So it does move. Okay. But under the heading of weight, there's more. There's a spring here. As you know, there's a spring here. And there's an anchor point, and there's a spring, an extension spring like that. Okay. And now the book shows it wrapping right around, but it's a little bit confusing. I'm just going to show it anchored to the 9 o'clock position. So it's just a steel strap on the end of an extension spring and just screwed into the perimeter of wheel A at 9 o'clock position. Okay. So of course it comes along for the ride. It's going down here, and that point, that attachment point, is going to wrap around counterclockwise. It's going to end up being wrapped down here somewhere, and the result is that the spring stretches further. Okay, so the red indicates the final resting place. Okay. Now, another thing that's otherwise implied in the question is that this wheel is rolling about the contact point with the wall. You don't know that for sure. If this wheel was made of ice and this was a block of ice and everything was wetted with water, there's nothing saying that wheel's going to roll. In fact, it could, in a bizarro sense, when this thing drops, the wheel could actually rotate clockwise because the spring is too strong, and it overcomes whatever minimal frictions at the ice-to-ice interface. Well, there's no mention of the thing being made out of ice. There's no mention of the friction coefficient here. It's implied, not my favorite thing, but it's implied that the wheel rolls counterclockwise down the wall. Maybe the wheel's made out of rubber. Maybe it's rubber. How is that implied? Because the author reminds you of the mass moment of inertia calculation for the wheel. He says the weight of wheel A is 80 pounds, and oh, by the way, the mass moment of inertia of the wheel can be calculated from 1/2 mr squared. Well, that right away is the author's way of saying, oh, wink, wink, nudge, nudge, it's going to rotate. You don't need the mass moment of inertia for something if there's no rotational motion. So it's implied that the wheel rotates. Okay, counterclockwise, no less. I mean, again, the full analysis of this in the absence of any friction coefficients would be pretty pronounced, okay? But we're going to take it with what's implied by the author. Not my favorite setup for a question, but okay. All right. The other thing, there's one besides the friction force being constant 20 pounds. There's one other little nice thing the author does, and the nice thing is that we're going to neglect the weight of the link. Okay, neglect link mass. That's huge because the link is in plane motion. It's simultaneously translating, right? It's slightly translating down, um, very little bit, and rotating counterclockwise. But we don't have to account for that plane motion because the link has no mass. So, and if the link was very lightweight, it's just in tension, you could just make the link out of a little strip of whatever aluminum. You could argue that that's not an invalid thing. So, all right, some dimensions to go on here. This initial triangle through here, okay, is a right triangle, and it's 10 inches tall by 24 inches that way. Okay, and then it says the block. Here's the RTF statement. Okay, the RTF statement says find the velocity of B after it has moved 6 inches to the left. Okay, so here's the 6 inches. Okay, another right triangle, and the link would look like this now. Okay, okay. Well, 6 inches to the left, that means this is 18 inches. Okay, that's all we know for sure there. Okay. One other bit of information: the spring has a spring constant of 1 pound per inch. K equals 1 pound per inch. Okay, and it's initially stretched. X initial is 2 inches, so it's initially stretched 2 inches. So the spring, some work has been done initially to stretch the spring 2 inches, and then it's further stretched as A progresses down the vertical wall and starts winding this strap around itself. It stretches the spring further, but we don't know how far. Okay, so the first thing we have to do after that, very first thing, which is take stock of what exactly we're up against, is let's do a geometry analysis. First of all, the length. That's the hypotenuse on the triangle. It's common between both. That's the common thread between these two, the red triangle and the purple, is the length of the link. It's the square root of 10 squared plus 24 squared. Okay. 10 squared plus 24 squared equals square root 26 inches. Okay. Then the second triangle. Now what I want to know is I want to know this distance right here. Because that is the change of potential energy of the wheel. We need that to track the energy. Also, it has something to do with how far the spring stretches. Okay, So that is the red triangle. Here's the red triangle, okay? This is 18 inches, 24 less 6. This is 10 plus, this is 10 plus y. You know, if I call that y, that's 10 plus y. And this is 26 inches, okay? So we have this going on. We have 26 squared equals 10 plus y squared plus 18 squared, okay? So 10 plus y equals, right, the square root of 26 squared minus 18 squared. You don't have to say 10 plus y. You can just figure out the triangle height. But here we go. 26 squared minus 18 squared equals square root 18.76 inches. Therefore, y is 8.76 inches. That's the distance that distance that wheel A drops. Okay. All right. Well, you'd think the question's over because that was a bit of work just to get there. But it's not over. Spring analysis, okay? The spring is attached to the 9 o'clock position on the wheel. The wheel's rotating about the wall. It's not rotating about the, relative to an observer, a stationary observer, the wheel is rotating about the 3 o'clock position, not the center axle, the contact point. So there's an easy way and a hard way to do this. The easy way is just to realize that if with this wall like this, and the wheel here at one point, and the spring attached here, and then the next point is the wheels down here, and the spring's attached here. The easy way to say it is say, well, if that moves 8.76 inches down, right, then the spring moves twice as far, okay? So by observation, and that would be known if you did some wheel analysis or so on. The top of the wheel has to move twice as far as the bottom, okay? But here it is with my attempt to do it with the S equals R theta analysis. Think of a link right here, okay? A link like that, and another link in the middle, one the smaller link. Let's draw it over here. Let's do the wheel like this. Okay, there's the rotational point. Here's one link to the center of the wheel, and then imagine another pinned link that goes all the way to the other side like this. Okay, so you got two links. Okay, link one has a radius of the wheel radius, which is 9 inches. Link 2, the red link, its length is 18 inches. Okay. Here we go. S1 equals R1 theta, theta A. Okay. S1 is 8.76 inches. S1 is how far the wheel moves down. In other words, how far the center of the wheel moves down, 8.76 inches. 8.76 equals R1 is 9 inches, and theta A is unknown. Theta A equals, okay, 8.76 divided by 9 is 0.973 rad. That is the displacement in radians counterclockwise of that little imaginary purple bar, the little link bar, the pin link that connects the center of the wheel to the contact point. That's common for the red link. The red link also moves through the same theta A. So S2 equals R2 theta A. Well, S2 is 18 inches. Sorry, S2 is unknown. R2 is 18 inches, and theta A is 0.973 rad. And we are going to end up with the same number initially. I say, hey, if you know your wheel stuff, you realize that if this wheel moves down 8.76 inches, the perimeter moves down twice as far. 8 is 17 point, what is that? 552 inches. Well, here it is here in mathematics. S2 is 18 times 0.973. Whoops, 18 times 0.973. 17.51 inches. S2 equals 17.51 inches. Okay. In other words, the spring is stretched. Okay. The spring. So thus, after wheel A descends 8.76 inches, the spring is stretched a further, because it's already stretched 2 inches to begin with, a further 17.51 inches. Okay. Uh, Again, a 2-to-1 ratio, and that holds for all wheels, of course. Doesn't matter what the diameter is, radius, and so on. Okay. Put another way, when you drive down the street, your axle of your car might travel 1 kilometer, but the top of the tire has traveled twice as far because it has to roll around and catch up to the road again. That's sort of a Timothy Leary moment, but yeah. All right. Okay. Are we ready to do dynamics yet? Because we're just really just doing kinematics and geometry right now. Okay. Step number 3. Initial energy. Here's the energy balance, conservation of energy. Okay. Here's the system. Initial energy equals final energy. Initial energy, well, it's all sitting there. There's no motion, so there's no kinetic energy initially. It's just sitting there. But A has a tendency to drop vertically. B will not drop, so there's no change of potential for B, but there's a change of potential for A. So initially A has energy, and then it drops down to some, let's call it a datum, okay, and all of its energy is used up. Okay. Also, there's an initial spring length. It took work to stretch that spring 2 inches. That work is energy in the system. If you suddenly cut the strap that holds the spring, the energy would be released and the spring would snap. That is energy initially. Okay, so the initial energy is spring energy plus potential energy of A. Okay. The final energy, well, this thing moves down, it's moving, it's rolling. Rolling, got that? It's rolling and moving down. That's 2 different forms of motion. Plus B is moving to the left. Plus there's friction. Plus the spring. It's just the gift that keeps on giving. Spring energy plus potential energy equals kinetic energy of A, linear. It's dropping straight down. It's moving straight down. It's actually A is in plane motion. It's a classic wheel, plane motion. Kinetic energy of A, I drew it to the right, but it's actually dropping. Plus kinetic energy of B, which is a linear. Okay, it's moving to the left. I'm just showing an arrow meaning linear. Okay, plus kinetic energy of A in the rotational sense. A is in plane motion, so it's got both linear and rotational. Plus, here it is, plus the work of friction plus the work put into the spring. This is a pretty doozy question. 5 things. Again, here we are. It doesn't say this thing comes to a stop. It says what's the velocity of B when this thing is dropped through whatever. It says when this moves to the left 6 inches. So when this thing drops 8.76 inches. Well, it's still moving. So it's got rotational kinetic energy, linear kinetic energy, spring is stretching, and work is being done against friction. 5 different things. 1, 2, 3, 4, 5. Okay? All right. A few things out of the way. Spring energy, okay, is 1/2 kx squared. You know that, okay? The spring energy is 1/2 kx squared. So here we go. 1/2 kx squared. Okay. Plus potential energy, well, that's weight times height. weight times, I'll just call it Z. Okay. Whoops, not plus, equals. So that's those two terms right there. That's the spring energy, potential energy. Kinetic energy linear of A. Well, that's 1 half mv squared. 1 half m a v a squared, right? By the way, this is the weight of A. Kinetic energy linear of B. Well, that's 1 half the mass of B, the velocity of B squared. All right. Kinetic energy angular of A. That's 1 half I omega A squared. Plus friction force. Well, that's force of friction times distance, which is actually 6 inches. We know that distance. And then the work of the spring, and it's just more work. It's just 1 half. This is initial, and then 1 half. This is x initial. I even said it as much. X initial, 2 inches. Okay. And this is 1 half kx final squared. Okay. That is borderline root canal level, but it is what it is. Okay. All right. We need K, we have X initial, we have X final, that's the 17.5 inches, or the 19 and a half, sorry, 17 and a half plus 2, but masses are easy enough. Okay, let's do a couple things here though. Where, okay, K spring, this value, it says one pound per inch. Well, let's normalize everything in feet, so it's 12 pounds per foot. Okay. If it takes 1 pound to move 1 inch, it takes 12 pounds to move 12 inches, aka 12 pounds per foot. Okay. The mass moment of inertia of the wheel. They give you the equation 1 half mr squared, right? So 1 half. The mass is the weight of the wheel divided by gravity squared. Sorry, m, that's mass, sorry. Radius squared, 0.75 feet squared. Okay, so let's get that. So some trivial sort of just laundry things, laundry list. Mass 80 divided by 32.2 is 2.48 times 0.5 times 0.75 squared is 0.698 0.699 foot pound second squared. Foot pound second squared. Okay, that's the moment of inertia of the wheel. Okay, x initial for the spring is 2/12 of a foot. It's moved 2 inches initially, and x final for the spring is, well, it's 2/12 initially, and x final is 2 plus 17.51. An easy one to mix up, but it's 19.51 twelfths of a foot. The final extension of the spring is 19.51 inches. So don't make a little oops there. Okay. Other things we can clean up here. So that handles the K and the XI. The weight of A is nothing. Z is easy. MAVA squared. And then point it like this. In a question like this, you stop and say, what am I doing again? What am I after? The velocity of B. Okay, the velocity of B. So the velocity of B is right there. I got everything here except omega A and velocity of A. So we have more relationships to explore here. The velocity, we have to relate the velocities together, okay? All right, omega A. How to do this? It's a floating link, okay? Floating link analysis to determine V8. Omega A is not omega of the link. Omega A is omega of the wheel A, so I don't need to worry too much about that, but it looks like this, okay? Here's the link at just some arbitrary angle. VB is straight to the left. Point B is up here, straight to the left. VA, of course, is straight down, right? Here's point A, right? The dimensions here are at the final here. Here's the red ink to indicate the final dimensions here. Here it is here. Here's the triangle that defines that link, right? This is 18 inches, and this length here is 18.76 inches. That's the height of the triangle, okay? And if you care about it, this is 26 inches, all right? So there's the velocity triangle, okay? And you can relate VA to BV with the instantaneous center. Here's the instantaneous center of rotation for that link, okay? And so about that link, about the claim to fame of the instantaneous center is that for a given body, that's the center of rotation of the body. Okay, that's its ground zero, if you will. It's orbiting around that center right now, and all velocities on the body can be related to the IC with perpendiculars. So it basically says this. So the link is the common thread here is the angular velocity of the link. Okay, the link is rotating this way, omega, and it's the instantaneous center. It says that the velocity of A, okay, is r. How does it go? Velocity of A is r omega. Okay, r a omega A. Okay, and the velocity of B is rb omega, and the omegas are the same. This is the same omega. So then you can say you can set up a ratio. You see that? Okay. So you can say VA. Now what am I doing again? I want to eliminate VA. I don't want to know VA. I want to know VB. I want to express VA in terms of VB. So I'm going to say VA equals, and I'm going to say VA equals RA omega. Well, RA and omega is VB over RB. So I just took these two, made one equation out of it. That's R. This is V. That's R. All right, so we have VA equals RA is the radius for instantaneous center is 18 inches. VB is the unknown, of course, and RB is 18.76. Okay. Therefore, VA, for purposes of substitution, is 18, right? Here it is here. 18 divided by 18.76, 0.959. The velocity of A is 0.959 that of VB at the final, right? At the termination of the question when A is dropped 8.76 inches and so on. VA is 0.959 VB. That's going to get subbed in up here. This big old equation right here, this one right here, okay? We have got our ducks in a row. You may not believe it, but we do. Okay? Again, reminder. Initial energy, initial spring stretch 2 inches. Well, we know K, we know XI is 2 inches, 2/12 of a foot. Down here. Potential energy of A, sitting there, trembling, waiting to drop. That's the weight of A times the distance through which it drops. That's an easy one. 80 pounds times 8.76 inches. Right? All that energy then is transformed into linear kinetic energy of A. 1/2 mass of A VA. Well, we're going to do that sub down here. We're going to put this VA right there, and that'll make that a function of VB squared. Right? This whole thing 0.959 VB will have to be squared there. Plus kinetic energy of B, moving to the left, 1/2 m and VB. Well, that's what I want to know. That's the unknown. It's going to be here and here. Plus the angular kinetic energy of the wheel, which is 1/2 I. We've got I figured out, 0.699 omega A. Now omega A, I go, oh, my bad, I need that as well. Omega A I can get that from here. I'll do that on the next page. Omega A I can express from this relationship. Omega A, it's right there. Omega A, sorry, that's not omega A. That's omega of the link. Omega of the wheel is, I'll do it in the next page, but I gotta get that one. Okay. Force of friction, 20 pounds times distance, 6 inches. That's easy. That's as easy as the potential energy. And then the final spring force, the spring energy is 1/2 K times the total extended length. Okay. All right. This is page 2. Let's get the omega for the wheel. Okay. Page 3. Also need angular velocity of wheel A after it's dropped 8.76 inches. Okay, that's not the same as this omega. That was the omega of the link. They're not the same. They're completely different bodies. Okay. Omega A can be related to the velocity of B. All right. Um, um, through this, we have this already. Oh, wrong page. Sorry. We have this already. V is 0.959 VB. Well, let's express VA in terms of the wheel speed. Okay. So the velocity of A. Okay. I'll just say this now. The velocity of A, the linear velocity of A, the wheel. Okay. Is equal to RA omega A. Right? But VA equals 0.959 VB. So I'm doing a substitution here. So we have this 0.959 velocity of B. That's the sub. That goes here. Equals the radius of A. Well, the radius of A, right, the wheel radius, analyzing this wheel as it rolls down this wall, okay, the radius is 3/4 of a foot. Not the diameter, the radius is 9 inches, 3/4 of a foot. Okay, just a simple rolling wheel analysis. The radius of A is 0.75 feet. Okay, omega A. Omega A equals, okay, do the math there, okay, 0.959 divided by 0.75. 1.279, 1.28 VB. All right, that is, I forgot to do that on the previous page. That, okay, that is going to go right here. Okay, are you with me? I'm not sure I'm with me, but all right. Step 4: input numerical values and substitutions into this box, into this equation. Okay, so here, let's go like this. Here's the equation. Okay, 1/2 the spring constant, 12 pounds per foot. The initial extension of the spring, 2 inches, 2/12 of a foot squared. So 1/2 kxi squared. That's the spring energy. Plus the weight of A, which is 80 pounds, times the distance through which A drops. That's the Z distance. That's 8.76 twelfths of a foot. 8.76 twelfths of a foot. Okay, that's the initial energy. Okay, that equals, and the final energy is going to be a bit of a mess. I'm going to put it down here. Here's the final energy. Okay, one half times the mass of A. This is the linear, the kinetic energy of A. Mass of A, 80 over 32.2. I'm going to leave off the word slug right there. Velocity of A. Oh, there's the first sub. That is 0.959 VB. 0.959 VB all squared. right? 1 half MA VA squared, 0.959 VB all squared, plus 1 half the mass of B. Well, that's 60 over 32.2, right? VB squared, well, that's the unknown. That's right there. That's what we're after. There's the RTF. VB, okay? That's kinetic energy B. Plus 1 half the mass moment of inertia of the wheel, right? Which is 0.699. I'm going to leave off the units. 0.699 foot-pound second squared, okay? 1 half I omega A squared, omega of the wheel, 1.28 VB, all squared. There's the next sub, okay? So that's this one right here, 1 half I omega A, omega of the wheel, all squared. 1 half mass moment of inertia of the wheel, omega A, which we've gone to the trouble of expressing in terms of VB, all squared. That's 3 kinetic energies, 1, 2, 3, plus the friction force, 20 pounds times 6 inches, 0.5 feet. That's the friction energy. Notice there's no such thing as a negative motion. There's no negative energy. It's just all positive. It's one easy thing about energy. It's all positive, okay? Plus the final spring force, 12 pounds per foot, 1 half, X final, 19.51 twelfths of a foot squared. Okay? Holy smokes. Not going to lie. Not going to lie. Here's the initial. I'm going to start up here and do some calcs. Okay? 2/12 of a foot. Whoops. Here we are. I'm just doing these calcs and I'll write the numbers down here. 2/12 of a foot squared times 12 times 0.5. Initial spring energy 0.167, 0.167 foot-pounds in the spring. Plus initial potential energy 8.76 twelfths of a foot, 0.73 times 80 pounds, 58.4. So an awful lot of energy, 58.4 foot-pounds of potential energy in the block. Okay, that equals the kinetic energy of the, what is that? Of the linear motion of the wheel. Okay, 0.959 squared times 80 divided by 32.2 times 0.5. 1.142 VB squared, 1.142 VB squared, foot-pounds of energy, plus the linear kinetic energy of block B. That's the mass of B, 60 divided by 32.2 times 0.5 is 0.932 VB squared, plus the rotational kinetic energy of wheel A. All right, that's 1.28 squared times 0.699 times 0.5 is 0.573 VB squared, plus the work of friction, 20 pounds times half a foot is 10 foot-pounds into friction, plus the final spring energy, 19.51 divided by 12, 1.626 feet squared, times 12 divided by 2, 15.86 foot-pounds in the spring. So the spring doesn't start off with a whole lot of energy, 0.167, but it ends up with a lot of it, because you're squaring the, the further you stretch it, the more it takes. So I think that's good. VB equals, oh yeah, simple calc, okay? Here it goes. Add up all the constants. VB equals the square root of 0.167. Let's put that up here. 0.167 plus 58.4 minus 10 minus 15.86 is 32.707. That's the constant. And then divided by the constant in front of the VB squared. I'm not spending a lot of time on the math here, okay? But in front of the VB squared, I have 1.142 plus 0.932 plus 0.573 equals 2.647. Okay. So again, I collected the constant on the left, VB squared is on the right. I flipped them. I put VB here as a square root of that. Invert that times 32.707 equals square rooted 3.52. VB is 3.52 feet per second to the left. I hope you enjoyed that. That's sarcasm, but there is so much going on in this question. If you can just understand bits and snips of it, it would be like, to be honest, if I did this on an exam, I doubt I would get the right answer. I would probably forget something or make a incorrect calc error somewhere. But that's a 3-page example. Very challenging, got to tell you. That's got a lot of stuff going on to it, but it's got everything in the kitchen sink as far as energy and kinetics and so on. Okay. Do your best. Look at it a few times. Just make sure you understand how I related the velocities to the angular velocities and so on. That's a critical skill in any question. You have to be able to relate a linear velocity to an angular velocity to eliminate unknowns. Okay. And the spring energy, make sure you know how to process that. That's also somewhat tricky. Okay. Otherwise, good luck to you all, and I'll see you next time.